So welcome to the first regression workshop in our machine learning workshop series, where the rest of the workshop will happen in week 4, week 6, and week 8. So you can find more information from IEEE, Triton Neurotech, or ACM AI. I'm the speaker today, and my name is Nova. We have Sunny from IEEE and Michael from Triton Neurotech, and they will help to talk about the topics today. So if you haven't signed up yet, I'll appreciate if you can do it really quick. You can scan the QR code on the slide, or you can get the link from the chat. What we're going to do in this workshop is that our final goal is to train a deep neural network that finds the height of a given baby using our baby data set. So finding the height of a baby can be useful to like parents or medical institutions. But more importantly, we hope that you can learn to build this network for more data and analysis for like your future projects. So yeah, now let's go to next slide. Yeah, so this is a link tree to Triton Neurotech if you want to learn more about the club. So let's just jump right into our notebook. I want to specifically thank Neuromatch Academy for their machine learning tutorials. They're very useful and explicit for people who want to step into machine learning. So they have topics from the basics that we will cover today, or like more advanced topics like transformation. So we will introduce that in our last workshop. Definitely check out Neuromatch Academy. So let's start with our agenda today. Yeah, so we're gonna talk about baby data set, obviously, and we're gonna talk about optimization, gradient descent, training testing data set, and deep neural network eventually. So let's start by introducing the baby data set. It consists of 836 silhouettes of babies and toddlers with their height specified. Let me run it real quick. Therefore, today we're solving a regression problem where the data set consists of only one group of data, which is the baby silhouettes. Or in other words, we're learning about the pattern of this data set. In the future, you will encounter classification, which is aimed for distinguishing more than one data set. For example, you're trying to separate dogs and cats. But we have only one group of data, the baby today. So our goal is to create a regression that returns a single floating point value equals to the height of a child silhouette in the photograph. So yeah, we're now moving on to optimization, section 2. Okay, perfect. So let's start from a 2D graph where the height corresponds to the weight plotting on y-axis and x-axis, and we assume that it is a straight line. So how do we find the best approximation of the height given a baby's weight? Well, if we look at the graph on the left, so yeah, look, exactly the graph that Michael is showing right now, we can see a line of best fit y equals to 4.36 plus 0.3x, given the best approximation for this random data set. Similarly to the graph on the right. So there are just two different examples of different data points. Okay, so now we know that if we assume height y and weight x of babies have, and it has a linear correlation, we simply need to find the red line or the line of best fit. Yeah, so to find our height for a given weight of the baby, for example, looking at the graph on the left, we can assume height equals like height y equals 10 when x, according to their units, equals to 20. Or actually, we look at x to find y. Yeah. So we're finding the function y equals ax plus b, where a is the slope and b is the intercept to the y-axis. Really clear. So my next question is, how do we find the line of best fit? Well, we can find the differences between one specific data point and the point which is predicted by our model on line of best fit. What I mean by that is like we're finding the differences of the y of data point and y of the model at the same x. This is called residual. So yeah, exactly. That line, that black line that Michael is showing. So if we collect the residual for each data point, we can know how much is different from our model for the entire data set. So what if there is a data point above the model by 5 units? For example, Michael, can you just point at any data that's like above the line? Yeah. And another one, it's below by 5 units. Well, if we are adding up all the residuals, they will cancel each other out. And that is problematic because we want to find the differences between all data points to the model, no matter the data set is above or below the regression line. So I want to introduce this method that is really useful called the mean square method, where we square the residuals for each data point. So the sign of residuals is taken out from the calculation. And then we divide that sum. We divide that sum by n if like there are n data points. So we get the mean of the squared. Yeah, so this gives us the average difference of a data set, and we will call this loss. This is very important. So you need to remember loss equals the mean of square residuals for a data set. Perfect. Recall our goal is to find the height given the silhouette of the baby, or here we simply to find the height given the weight of the baby. And we can make a prediction by finding our loss. So we can all agree that the smaller the loss, the more accurate the prediction is, because the average of the differences between data points and our model means the closer they are, and we're aiming to have a model that is closest to our data set. In other words, we want to find the minimum of the loss. So what we're going to do next is to see how we find the minimum amount in loss. And we have a 2D loss function given by the graph that Michael is pointing right now. And we will apply the same idea to loss function that have more dimensions. For example, like 3-dimensional graphs. If we graph the loss function, So if we have this 2D loss function given by the graph, we can really easy to find the minimum by deriving the loss function equals to 0, which is the red line show. It's the global minimum. Yeah, and this is called the direct solution. So we can do the same thing to the 3-dimensional graph now. If we graph the loss function in XYZ coordinates, we can find the minimum in z-axis from x-axis by partially deriving the loss function by x. And we do the same thing to y-axis by partially deriving the loss function by y. So we can find the minimum z-axis by moving towards 0 in both the partial derivative of x and y. So if you look at this graph, you can see two arrows it's from the top of the mountain, and it's like sort of climbing down. You can see two arrows. One is like going the direction of X, and one is going the direction of Y. And that shows that adding up two different vectors or two different directions gives you the next points that like going towards minimum. So yeah, this is the idea. Yeah, so the same idea always works to find loss function, even in like higher dimensions. Like there are millions in deep neural networks. So we can no longer calculate it mathematically because it is like becoming too complicated. So we will introduce another effective method to deal with this issue called gradient descent. What to remember from this section is that we can find our regression by finding the minimum loss function.
Yes. Now that you know the concept of the loss function, and our goal is to minimize the loss function, gradient descent is actually an easier way to do it. Let's take a look at this graph. Suppose this is the curve, the entire curve is a loss function. For the sake of simplicity, we have made it one dimension, and it's a little easier to look at to find the minimum. So let's take a random point on the loss function, the yellow dot here. Remember, our goal is to find the minimum of the loss function. So what we can do here is to apply the gradient descent method. The idea of gradient descent is to take the repeated steps. As you can see, there are many red lines here. They are steps. In the opposite direction of the gradient of the function at the current point, because this is the direction of the steepest descent. What I meant by that is for the current point, let's say the initial point, yellow point here, if we take the gradient, which means we can find its slope. This will be the steepest descent that it could take. So, but you should know that the tangent line, which is the gradient, is positive because you know the slope. This is positive, this is negative. So if this is a positive, we don't want to keep climbing up, right? We want to climb down. So because we can see the minimum is here, so we want to approach to the minimum. However, this is positive. So one way we can do it is to add a negative sign in our function here to make it negative, just so when it moves, it always moves to the minimum instead of the maximum. So if we follow the opposite direction of the gradient of the function, we must find the minimum of the function. Notice that gradient descent method doesn't guarantee that we can find a global minimum. Most of the time, we can only find the local minimum if the function is rather complicated. Like I said before, this is a simple function, so we can just by eye looking at it, we can find it. So another analogy would be of the gradient descent method would be suppose there's a person stuck in a mountain. So suppose there's a guy here, and he's trying to get down, which means he wants to find a minimum. It's at night, so that the visibility is extremely low, so he cannot see this directly. He cannot see it, but he can see things that are around him. So he only has the local information. So to get down to the bottom, one way he can do is he can use the gradient descent method, which involves in looking at the steepness of the hill at their current position. So then proceeding in direction with the steepest descent, which means downhill, using this method, they will eventually find their way down here, all the way to the bottom. Oh, sorry, all the way to the bottom here. So this is the intuition for you to understand the gradient descent method. Okay, so for the entire vanilla algorithm, because we want to update the W. So J is the loss function, it's in terms of W. So once we found a best W, we found the minimum of the loss function. And then, so the entire vanilla algorithm depends on the epoch. So epoch is another important terms in machine learning. For now, I will explain later. For now, you can think it as the times that we run this algorithm. It's going to be how many steps. So if you want to run 1 steps, you can set the epoch to 1. If you want to run multiple steps, you can set the epoch to anything you like. Just remember, 1 epoch does not mean it's good. Usually 1 epoch is pretty bad here. We usually set multiple epochs here. So the learning rate here, can you scroll down, Michael? Scroll down a little bit. Yes. Okay, let me clear this. So the learning, we have introduced the basic of gradient descent so far, but you might be wondering what the Greek letter eta here. Eta here is what it is, right? So this is the step size. Oh, sorry, that represent the learning rate, and the learning rate affect the step size. In setting a learning rate, so step size means how many steps you want to proceed for each step. So setting a learning rate is really important. There is always a trade-off between the rate of convergence and divergence. Divergence means you did not get your expected result. While the descent direction usually determined from the gradients of the loss function, the learning rates determines how big a step is taken in that direction. A too high learning rate will typically jump over the minima. As you can see, it's just jump from here all the way here, but expected is here. So we skip it. So this is not good. So a too high learning rate will cause that. But a too low learning rate will either take too long to converge, or sometimes it was stuck in an undesirable local minimum. So finding a just right learning rate or a step size, finding a just right eta is very important, just so we can converge at the right speed, so we won't waste a lot of resources, and it won't be you won't give us an unexpected result. So this is the learning rate, and so an optimizer. So the last thing we're going to talk about, not the last thing, but last couple of things we've talked about, optimizer. So you can think of gradient descent as sort of optimizer, but more specifically, the optimizer can be thought of as an add-on of the gradient descent to make the gradient descent process faster and smoother. So there are many optimizers out there, with the most popular one being Adam. But in this tutorial, we are going to cover momentum, which is the backbone of the Adam optimizer. So as you can see in this graph, although gradient descent, we just talked about it, is a very popular optimization technique, we can find a minimum, but sometimes it would take such a long time to process if we have some extremely poor dataset conditions on data sets. So sometimes when you drop into the local minimum, let's say you drop in here, the gradient descent method will be stuck at that local minimum. Essentially, so this is a global, but if you're using gradient descent, you're likely stuck into it. So, and there's no way for you to get up, which is mean that is not the best option. It still works, but it's not the best option. So using gradient descent can cause that. But if we're using an optimizer named momentum, can fix that issue. So essentially, Michael, can you scroll a little bit down? Yes. So essentially, when we're using a momentum, I can give you another analogy to give you some kind of intuition. So suppose there's a hill here. There's two hill here. So if a ball, so this is the W. So if I push the ball downhill, the ball accumulates momentum as it rolls downhill. So when it's going down, it becomes faster and faster on its way. So it becomes faster until here. So that means it accelerates along flat direction, meaning if it doesn't change the direction of rolling, it would accelerate. However, when it reaches the minimum point, whether it's local or global minimum, it will change the direction, right? It start rolling upward, right? Once it changed the direction, it started to slow down along with the slow down. So it would be slowed down to, So it's slow down here, but it will go beyond the minimum point. That's why the momentum method can ensure us to ensure the ball, which is W, to go beyond, a little bit beyond the minimum, so that we can see a further, if there's another minimum that is more minimum than the current minimum. Like in this case, this is more deep, right? Deeper than that. So there are three advantages. And also, sorry, if you see here, it's slowed down along the sharp directions, meaning if there's a direction changing from downhill to uphill, then it's going to slow down. So, and you can also see this plot. See this plot here. As it's changing the direction, it's gonna slow down. But as it found the flat direction, it's gonna speed up. So there are actually three advantages of the momentum that you can imagine. First, it converges. We have a faster convergence. That means we can use less resources to do the same amount of thing that the gradient descent can do. The second thing would be reduced oscillation. As you can see here, the gradient descent typically give you some oscillation along the way, but using momentum, you won't have such phenomena. The third advantage is, well, it can go beyond the local minimum to find a further minimum that can helpful to find a actual, that is optimal minimum of our loss function. So this is momentum, and they are pretty useful. Michael, you want me to go over that?
Nova, can you go over overfitting and underfitting?
Yeah, of course. So before we build a deep neural network for our baby data set, I want to quickly introduce a method called train test split. This method helps us to avoid overfitting. So what do I mean by overfitting? Overfit happens when we do very good on a training set, but really bad on a testing set. Optimum, on the other hand, happens when we do very well both on training test and testing set. And underfit is the opposite of overfit, where we did really good where we did very good in testing set, but we did poorly on training set. So to avoid overfitting, we want to split our data set into three parts: the training set, validation set, and the testing set. We use a training set to find the pattern of our data set, and then we will use a validation set to check if we're like overfitting. So after that, we will use testing set to finally see whether it works well, like the accuracy is well on the data set that we never touch on. So we will split our data set when we implement a deep neural network.
Yeah, Sunny, do you want to expand the effect of epoch for overfitting and underfitting?
Sure. Let's give me a second. So the epoch, like I mentioned before, is a term used in machine learning and indicates the number of steps that you want to take. So in practice, we would want to use more than one epoch, more than one steps, because sometimes it's not enough to pass the complete data set only once. And it's impossible for you to go to the minimum by stepping only once. So we need to pass a complete data set multiple times, which means multiple steps, just so we can obtain the best fitting, like the graph you see here, the middle one, the optimum. This is the best fitting that we are expecting. One epoch typically causes underfitting, which means the model is bad. It cannot even train your training data set well. Too many epochs typically cause overfitting, which means the models the training data too well to test it on another testing data set. That means on other testing data set, it behaves so bad. So just like a learning rate, choosing a right epoch is also very important. Yes.
Okay, now we have covered gradient descent optimization, as well as some hyperparameters such as learning rate and epoch. I think we are ready to start going over the deep neural network architecture. So just, take a step back and just zoom out a little bit. Let's see a broad view of what a neural network looks like. So a typical neural network consists of three types of layers. You have the input layers, and in this case, or the example we introduced earlier, the input is, for example, the height of a person. And we also have the output layer where, in the example provided earlier, is the weight of a person. And we have some hidden units in the middle to learn some complex representation of the data, which we will go more in depth later on in the workshop. But just keep this architecture in mind where we have an input, we pass our data through some neurons and hidden layers, and we arrive at our output. So let's start with an example of two-layer DNA with no hidden layers. Then our DNA will look something like this. We have our input data, which is the height of a person, and output data, which is the weight of a person. Then our model will output y equal to w times x plus b. So w, you can think of it from high school algebra, that's the slope, and b is the intercept in terms of Cartesian plane. One terminology that machine learning practitioners use for the slope is actually called weight, and for b, or the intercept, is known as the bias. And our predicted weight is going to be y equal to wx plus b. So now let's have a scenario. Let's say the weight of people we want to predict are from an alien planet, such as Alpha Centauri, and where people's weight is exponential to his height due to the weird atmosphere pressure in the alien planet. So here, let's look at 10 people's weight and height data. And we can see we have 10 data points, and very clearly we see an exponential relationship between the height and the weight. So now, what if we use a model architecture that is the one shown here, y equal to wx plus b? We see that we're trying to fit an exponential data with a very simple bare-bone linear model. And as we can see, it's a very poor fit to our data set. So what should we do to improve the performance of our model to better fit the data? It turns out that we can actually apply another function, g of x, to the output of y to learn more robust model. And this function, g of x, is what we call the activation function in machine learning terminology. So we see this here, g of x, I define it as x squared. And x squared is an arbitrary choice because I see, the data looks exponential. So I just pick an arbitrary activation function x squared. as our activation function. So now y is, instead of y equal to wx plus b, we're going to have y equal g of wx plus b. And we expand the terms based on the rule of g of x. We get, the w squared times x squared plus 2wbx plus b squared. So as we can see here, now we have an x squared term. So supposedly we're able to, model this exponential data better with the addition of activation function. And indeed, we start to see this curve thanks to our activation function. However, the question is, yeah, the model seems doing pretty okay. The question is, can we do better? Can we somehow make our model even more powerful than what we have right now, a 2-layer with an activation function? The answer is we can. The way we do it is by introducing something called hidden layers. The hidden layer is you can think of it as the auxiliary layers, auxiliary unit in the middle of the network in order for the model to learn more complex relationship. So here we introduce a hidden layer with one hidden unit. So again, we have the height of person. We're going to pass it through the activation function, in this case, g of x equal to x squared, and we get the output h of the activation function. Then we're going to feed h to w2 and then have our bias term and pass everything through another activation function. And that will be the weight of our person. So if we were to expand out the terms y here, we can see that now we have C1, C2, C3, C4 are just some real number constant. X4, now we have the x to the fourth term, x squared term, x term, and the constant term. And now with this new model, we're supposed to be able to model our data in a more robust way. And as it turns out, we were able to model our data perfectly with the introduction of one more hidden layers with one hidden unit. So now before we move on to how do we actually code up everything in PyTorch, let's just go back a little bit and start thinking about the idea of overfitting and underfitting. So as Sunny and Nova introduced earlier, if our model is too robust and it overfit on the training set, it's not going to generalize well to the test set in production when we actually ship our machine learning model for companies, and why not? So our goal is trying to find the optimum model that both generalize to both the training and the test set. And the idea is that on the spectrum from underfitting to optimum to overfitting, the more layers we have in the model, we are more prone to overfitting. The less layers we have, we're more prone to underfitting. And this is actually the same thing with neuron. So here we only have one hidden unit, but in reality, we can have more hidden units than just one hidden unit. And along with the spectrum we see here, the more hidden units we have, the more likely the model is going to overfit, and the less hidden units have, the model is less likely to underfit. So you might be wondering, so how many hidden units we need? How many hidden layers we need? The general rule of thumb is to pick the number of hidden units that is between the number of output and input neurons. But in reality, it's just trial and error. You just try, if you see model underfitting, you increase layers and increase neurons. If you see the model is underfitting, you increase you increase number of layers and number of neurons, and vice versa. So last question we want to ask is, like I said before, I pick an arbitrary g of x equal to x squared as our activation function. But that is so arbitrary. What is the activation function that people use in production, like in literally majority or almost all of the machine learning models and state of our machine learning model? So now Nova is going to introduce this activation function to you, which is called the ReLU activation.
Yeah, so ReLU is an useful activation function that we're going to talk about it a lot today. So it is a nonlinear piecewise function that outputs all positive inputs, aka y equals x if x is larger than 0, else y equals to 0. So yeah, let's take a look at the graph. So it's very useful activation function for several reasons. First, it is easy to implement using the max function. Here you can see that if we just use the max function with input 0 and z, it will output z when z is bigger than 0, and then it will output 0 when z is less than 0. So secondly, it is quite similar to our linear regression, looking at the positive part where x is larger than 0. So it will be a good tool when we try to build a deep neural network at the end of this workshop.
Yeah, so we're going to now start coding deep neural from scratch. And there's two main languages that we can use. One is PyTorch and another main one is TensorFlow. In this tutorial, we're going to use PyTorch because it is more intuitive and you're going to see, everything we talk about in the workshop being used in the implementation of building a model in PyTorch. So let's just first introduce our data set. So our data set is going to have some images of babies, and these images are grayscale images. It means that it's only going to be 2-dimensional, image width by image by height, instead of image width, image height by 3, which is the RGB value. Also, the image is on scale, so it's from 0 to 255. And sometimes people scale their images to 0 to 1. But the image data that we get here is on scale. So if we view the shape of our data here, we have 836 images, and each images will have one height data, and of course, the corresponding images. So if you just play around this code by running a few times, you can see, the different height corresponding to the different images. So first thing we do, so a big thing about machine learning is we try to reduce the bias of our model as much as possible. Earlier, we talked about chain test validation. That is to reduce our, the bias of our model. When our model is overfitting, we have a strong bias of our model. So in order to reduce bias, actually the first thing we do is to shuffle the data, because there might be some implicit underlying patterns in how the data are being sent in. So we simply just shuffle the data before we do our chain test validation split. And this is just one simple function to convert the NumPy array to PyTorch tensor. Because in order to work with PyTorch model, all the variable have to be in PyTorch tensor. Now we're going to split our chain test validation into 80% training set, 10% validation set, and 10% testing set. Usually we want the validation testing proportion to be higher if we don't have a lot of data, and we want, if we have, let's say, 1 million data, we can keep this proportion like 1% or 2%, because 1% of 2% of 1 million data is still a lot of data. But for the tutorial, for this workshop, we're just going to split into 0.8, 0.1, and 0.1. So now, building our model. So first, again, the first thing we're going to do is to flatten our 126 by 126 images. So if you can imagine a 126 by 126 image like this, we're just simply going to take each column and then just append them into a one-dimensional vector. That's the first thing we're going to do. So now the input layer of our neural network is going to have 126 by 126 number of neurons, and that's what this flatten function is doing here. Again, we have the ReLU activation following, that's our g of x. And then right after that, we're going to create a first hidden layer, and the first hidden layer is going to have 200 number of neurons. And then we're going to create another hidden layer with 200 number of neurons. And then finally, we're going to create the output layer, which has output size of 1. So this is going to be our model. First, the image will become flattened, and then it's going to pass through several hidden layers to learn some complex functions. And then eventually we'll have a single output that's the height of the images. So any questions so far from people? I don't see there's any question. Okay, no question. Okay, then we'll continue. So we instantiate our model by calling the constructor function. And by forward is pretty much will propagate the input data all the way to the output. And each forward will just, do this propagation. So images will be transformed to the output space. And that's what forward does. And now we're going to create a loss function. Earlier, Nova explained mean square loss. So this is literally mean square error loss. We can implement it ourselves using the formula 1/n times, the square error of the prediction and our y value ourselves. But here we're just going to use the PyTorch implementation. And again, we have to pick an optimizer. Like Sunny mentioned before, optimizer allows our loss function our gradient descent to descend more smoothly and more efficiently. And the one we introduce momentum and atom built on top of momentum and IMS prop. And here we pick a learning rate. And again, this is a hyperparameter, which means we might have to tune it if our models start diverging like we see earlier. So this value is very sensitive. So just make sure to tune it for your own purposes. Now we pick the number of epoch. And in this case, I have run the model before, and I see the model start overfit after 200 epochs. So I'm just going to set the model to 200 epochs because it starts overfitting afterward. So now for epoch in number of epochs, that is the equivalent of this line of code right here for t equal to 0 to t minus 1, t being the number of epoch. And we're going to update the weights. But before we update the weight, we first have to calculate the gradient in respect to different weights. So you can think of it as the slope, the intercept, and the other parameter. We have to calculate the gradient of each weight. So that's actually the first line of code we're going to have. So we enable the train mode and the eval mode. So this is just some PyTorch thing where when you're training, you enable the train mode. You're evaluating, or you're not updating, you enable the eval mode. So first thing we do is we propagate our network using net. So when you code net, what happens is it's gonna call the forward function to get the output. And then it's going to calculate the loss. And the loss function here is mean square error. And then from this loss, it's going to perform, chain rule. And chain rule will just go from the loss to calculate the loss with respect to each weight. And so the backward function here is calculating the gradient of each weight. So loss.backward is exactly this step here, gradient of loss function with respect to the parameter. Now, next thing is to step. So what do we mean by step? Like we mentioned earlier, we're taking a step toward the descent. So here, the minus learning rate times gradient is the step we're referring to here. We're taking a step in the direction of the descent. Next thing is we're going to, once we calculate the gradient and then we update the parameter, we have to zero the gradient because the gradient is by default accumulative over the number of epochs. And we want to refresh the gradients each time we train a new epochs. So we have to make sure we zero the gradients. And then we can simply get the loss by calling loss.item, and we're going to print out the loss as well as the validation loss after every single epoch, like shown here. So we can see early on the training loss and the validation loss are very high, but it starts to wind down after about 200 epochs. So here is the training loss and validation loss of our model. And then finally, we're going to see how well it does on the testing loss. And I think there is some error here because the test loss should not be so high compared to the loss and validation loss. But the main point is that if we see here, this is what we do on the testing set. We can see that here 86, 57, it doesn't look too good. 50 to 53.8, it's okay. We can see that the model is doing like a very okay job, but it is by no means a good job. It's because we simply cannot use DNN alone to learn images. It's not powerful enough. So in the next workshop, we're going to introduce something called the convolutional neural network that will significantly improve the performance of our model. So until the next workshop, I will see you there. So that officially concludes our workshop. If you guys have any question about the club, future workshop, or anything with regard to this current workshop, just ask away.
Yeah, thank you for coming. This is the end of our workshop. Our next workshop will be on January 25th from 6 p.m. to 7 p.m. And it will cover CNN, which is another neural network that's working better than CNN. Thank you for coming.